Good evening. This is a retake of the lecture from yesterday evening, Tuesday, September 2nd. I'm sitting at home now, so my cuckoo clock just bonged in the background, which you may have heard. But what I want to do is redo the first part of the video. I had some technical difficulties with the new classroom and the high-resolution monitor. So now I purposefully, at home at least, and probably next week in class, will make sure I force the system, both the display system and my tablet, to work in the lower resolution, which is a necessity for my older tablet. It has a hard time capturing videos at such a high resolution. So we're sitting here getting ready to go over a few types of materials that we did not do the last two sessions. This will end in less time than what it was recorded at last night, but I want to get to the transition point as quickly as possible, and then we'll switch over to the video that was captured after I made the resolution change. So for starters, I wanted to talk about a background of where DSP is used in practice. So I'm going to jump back over to the lecture notes. And this was the lecture 1. This is key application areas. Most of you know DSP finds lots of applications, but this is just a quick overview of things that we find where DSP system level design takes place. So computers and internet, we have broadband access, cable modems, we have voice over IP, which has been around for a long time, but that involves audio signal processing and then converting it to IP packets. We have high quality audio formats, MP3s, I'll mention that a little bit later. And then we have storage. We have very high density storage available now, and I had a student from Keysight back in fall 2022, my last master's student, who was working in that high-density storage medium, and we did some pretty interesting work, or he did, and he was working on that through his work, and then with extra things I had him investigate, including very high-speed modulation schemes. It uses what's called pulse amplitude modulation, PAM, which has got 4 levels as opposed to the older 2-level, and then because this is on a backplane, there was some transmission line modeling for getting the data in and off the disk. So that involved more than just DSP, but it also involved some microwave circuit design. Clearly big areas, mobile communications, using cell phones, over 200 million phones per year over the world. That's quite a few years old, that number, so I'm sure it's at least that large. Real-time compression for voice and video, things that we rely on a lot. I make mention of that because I think last night when I went through this the first time, I made the comment that we know voice and video are coded separately in HDTV today, and one of the things that I notice in particular is if you're watching a program on HDTV, you will frequently see that although the streams are carried in different parts of the transmission, the voice and the video part, they do get out of sync. And it is, to me, very annoying when the voice and the video are out of sync. That's just something that the technology allows to have happen. I'm not sure how to make that foolproof, but that's part of the compression in order to save bandwidth. 5G and 6G are, pushing out. We'll eventually be having 6G, but we have a lot of signal processing there at the baseband level, but more so at the RF level, where we can do things with the newer infrastructures. We can have antenna arrays to focus beams on certain users in the cell that you're sitting in, and the processing of the IQ samples, the actual digitized RF signals can be processed at a different location. So there's a backhaul system that moves it through fiber optic to a processing center separate from where the tower might exist, and that's some interesting technology into itself. I put the last bullet in here, commercial aircraft Wi-Fi. That's something that's been advancing over the past several years, and if you travel in a commercial airliner, they usually notice, I made 4 trips this summer, so either your aircraft has it or it's supposed to have it, and they'll say something like, ours isn't working just yet, but that's something that consumers are after, the ability to stay connected while they're flying on a commercial flight. And there's interesting communications theory aspects to that, and then just the in-aircraft distribution of the Wi-Fi signals. In industrial, I've got grouped into that, medical signals. That's been big and continues to be big when we're going into imaging with ultrasound for medical applications, MRIs for looking at parts of our bodies when we're under medical investigation for some issues. And then there's also a lot of DSP and virtual instruments for test and analysis where we can do things remotely. In my work right now, it's common that we have remote access to laboratories, and some of that involves some interesting processing capabilities. Moving down into audio streaming over the internet has been big. It continues to be big. We take it for granted these days. Home audio theater systems. So there you have drivers that can drive out to the transducers, namely the speaker systems, but also the processing in the box itself. Noise canceling capabilities, not only in the earbuds that you might wear, but forming quiet zones with noise canceling, say in the interior of a car. Soundstage and studio audio processing continues to do very well and is very important. I have an interest in that since I play as an amateur and I'm interested in protecting my hearing. So I have a device that I mentioned last week, the Bella Gem, is a device I'm sponsoring to eventually be trying out some ideas for a system I want to create for an IEM, which will be off the shelf, an in-ear monitor, but then drive it with different sources. One would be a source off of my horn that I'm playing, and then some near-field microphone to pick up the sounds, say in the section I play in, and then another microphone that would pick up more of the entire ensemble, and then form a mix for me, which is what the professional equipment does, but I want mine to be a low-cost solution. Video imaging, I think I already mentioned that. Biomedical, lots of possibilities there, and one of the really fast-moving areas is hearing aids and hearing assistive devices, more than just the, say, prescription hearing aid, which is maybe $3,000 per person, but something that can be very effective but not be at such a high end. There's lots of opportunities going on there. In automotive, we have engine control, which has been in existence for a long time, but now with the advent of electric vehicles, we have battery management systems. Dr. Platin Trimboli in the department work in that domain. Interior electronics, audio and graphics is also a big thing. And the number 4 on the list is probably one of the biggest, moving very quickly, is ADAS, Advanced Driver Assistance Systems. That's based off of millimeter wave radar, LiDAR, and camera systems. This is important in safety and driving, and if you have a vehicle that's not too many years old that you drive or your family does, it probably has some ADAS capability in it, and it's advancing very rapidly. Everybody's in competition with their millimeter wave devices to not only help with your cruise control, but help assess other vehicles around you and being able to determine their velocities from Doppler and location. And then the final is military aerospace. That's been the founding area for all of DSP for over 60 years now. And most everything in the consumer realm got its start here, like the millimeter wave radar systems were used in military applications, but they've been commercialized for the ADAS marketplace, surveillance systems, smart weapons. Something that I've always been interested in and continue to play around with a lot is this last one, software-defined radio. It's fun, and it's a nice hobby topic to work on. I actually have on this tablet, I've got GNU Radio Companion installed in my Windows subsystem for Linux, so I can use that, and then I can interface USB radio devices right into the Linux, and then play with algorithms for both transmitting and receiving modulated carriers and things. Okay, we've pretty much run the gamut on that. I will eventually come back over here, but that's going to be in the lecture that was already recorded last night. But what I do want to do is bounce back over to things on the website. We haven't spent any time talking about how you're going to get Python set up on your home system or your laptop. So we'll take a look at that. We'll sort of enter that domain by starting in the syllabus. And in the second page of the syllabus is where I talk about software tools that are relevant for the class. So Slack, we've been through that. Everybody's set up on that. The next one is setting up Python via Miniconda. So we're going to explore that a little bit right now and see where that can take us. It carries on in the part of the video that was recorded last night, and we'll follow up this new part one of the video. Something else we'll come to later in the lecture, and I think I may have introduced at this point too, was the use of types. And people have been kind of hinting at, or I'm sensing the feeling that that you have to turn in your homework to me on Slack as a PDF. So you have a challenge there, but I know it can be done. It's been done since COVID for my teaching, where you have to take maybe handwritten solutions, combine them with some computer code as proof that you've written code to perform some simulation or modeling, and then the graphics from the modeling tool, say Python or WX Maxima, whatever tool you decide to use. I'm going to advocate primarily using Python, but at any rate, this tool is in the cloud, and its primary focus is to write documents in a cloud-based environment and then export them out as PDFs. And you can composite things together from code. And since I presented the lecture last night, I forgot about another aspect of it, so I may make a brief mention of that. I think before I'm going to look at Miniconda, I'm just going to go look at the types link right now. So it should be connecting me. What I want you to do, if you would take on this challenge, and I know already because I taught the class through to the end last night that people are interested in this, and you were interested even more once you saw it. So first thing you have to do is get signed up and create an account. So you can create an account, and then you can access in the cloud. So over here, we could do my sign-in to types, and then I will quickly go look at my sample project. And now on the website, there is a link to get this sample project, which is a zip package, which will give you the files you see here, including a folder of figure files, which are used in my sample document, a template, which is a fixed hard-coded that you don't need to touch unless you want to modify the template, and then the main body of the document is in here. So there's a preamble just like there is in Python or even in WX Maxima and in Julia, where you're loading packages and resources to run the tool. So one of the things I didn't mention last night, but I'll mention now that I don't have included in this particular preamble, is the importing of a package which allows you to import portions of a Jupyter notebook. So that's kind of experimental, but I will want to revisit that again later next week. But by putting the import for that up here and then importing your Jupyter notebook right here into your document, you can selectively take cells from that notebook and embed them right into the document. So that slipped out of my mind last night because I was kind of rushing to even prepare this yesterday afternoon, this sample document, but we'll revisit that again. The bottom line, though, is as you'll see later, you can import content, and then you can import, it generates the table of contents with the links, but then you can import some problem statements if they've been scanned or available by another means. Those can get placed in here, and then you can write out your document, either write the text and the math equations, and if you have partially handwritten and partially typed in, those scanned in pieces are brought into here. And I give an example of just bringing in pieces of code either from WX Maxima or down here a chunk of Python code that has some results in it. So this appears later in the video, so I'm going to fall off of this for the time being, and what I want to do is focus on what was in the syllabus. And I guess that got lost when I followed that link. We were looking at the syllabus, and we were looking at the first step in getting Python in your system is Miniconda. So Miniconda is just a small version of the Anaconda environment, which has been around a long time. So I'll follow that link right here, and talks about installing Miniconda. So the thing when you get to the Miniconda will be about commercial setting. We're in education, so we're going to not worry about that. You'll be able to install it, and in particular, if you're on Windows, which I think everybody told me last night they were, you will follow the links underneath the Windows installation and get it installed on your system. You'll have access to add more packages, virtual environments, and manage it using either the PowerShell in Windows or the terminal, command terminal in Windows. That's the most common way. If you're in Linux or Mac OS, you'd be using a bash shell, for example. But those details are managed not in here. They're managed in here. So we look at this document now, and this will take us until we get ready to change to the video that I recorded last night. So get up to the top of this. So once you have Miniconda installed, I think I'm going to take a short break here. My son has just come home, so I'm going to pause the video and resume momentarily. Okay, the commotion is over with the dogs getting excited about somebody arriving home. So you get Miniconda installed, and you'll have something like this in your Windows environment to either run it from PowerShell, an Anaconda PowerShell prompt, an Anaconda command prompt, something along those lines. I mean, the way you would find that out is you would go into here, and then you would find this menu, and then we would see the options, just like I showed you in that screenshot. So that's how you get in to get your command prompt. And for me, I use PowerShell. So Windows PowerShell for me is over here, and I'm just going to open up a clean copy of the PowerShell and just show you what the steps are for getting things going once that starts up. So what you want to do is create a virtual environment. There will be a base platform or base install of Python that comes with Anaconda. You don't want to use that for installing packages into. You want to just keep it pristine and instead create a virtual environment. So that way, if anything gets messed up in your virtual environment, you can delete it and use your base installation to create another virtual environment. So I kind of talked through that here, but we're going to create a virtual environment called DSP-COM313. So the very first line that you do once you get into the command prompt is that. So over here, I'll clear this, and you can see from the prepending of the command line right now in the PowerShell, it says base. So what I want to do is just do conda, and this is talked about in the notes, conda environment list. So I'll list my virtual environments. And for me, I've already created virtual environments, so we're just going to see a listing of what I've got on my system. And a couple of weeks ago, I created the COM313, the newest version of Python. Last year, when I taught this class, I was using Python 3.9. So, but right now, you can see I'm sitting in the base environment. So I have to go conda activate, and then I have to list off which environment I want to activate. So it's DSP-COM313. And now you see I'm prepending with 313. If I do a conda list, I will see all the packages that are installed with this environment. And so when I grew this environment up from the starting point, which is right here where I just created the base environment, once it's done, then it tells you that I need to activate it, which is what I just did, and then I start installing packages into it. And the first package installation string is to install NumPy, Matplotlib, the graphics library, and SciPy. And then the second round of installations will be JupyterLab. Third round of installations will be IPyWidget, so we can have graphical GUI control elements when we do real-time DSP and work with sliders and buttons in particular. The next install is my package scikit DSP-COM, and I'm asking you to install 2.1. That's the newest version. I did a pip install because it was not on Conda Forge as a repository, but I believe that's been cleared up. So a conda install would do the same thing. Then after that, we want to get the tools for real-time DSP, and that's based on PyAudio. So we can install PyAudio. Reading through this, I'll let you do that on your own, that install PyAudio using pip. And then when you get done, this is just a snippet of the list, but what we were looking at over here in the terminal window, you can just scroll up and down. You can see in alphabetical order what we've installed. So what jumps off the page for me would be scikit DSP-COM. Did that get installed? And so we look under the S's. Sure enough, there's 2.1. PyAudio should be up here. Version 0.214. This was a package developed at MIT. It's not been really growing very much, but it's stable. Even though it's not a full version number, it's been working well for me for quite a few years. And some of the other packages we put on, like Jupyter, are in here, and so on and so forth. So this is really just, you can do maintenance in this area if you want to, and if you want to understand more about what Conda itself does, conda-help will give you all the command line calls that you can make for packages and stuff. And in my helps over here, I also walk you through some testing, and we're going to do a test of Pi Audio on my system perhaps next week, just so you can know how to test your own system, but you can read that. And last but not least, there's deleting a virtual environment. So that's mentioned here, how you would do that. This is a do it and it's gone. So it's fatal if you're doing it not intentional. But what will happen is you'll sit in the base environment and you'll say, I want to remove an entire package, an entire virtual environment. You can always create another one. And if this one ever gets corrupt, the idea would be you would create another one. Maybe give it a different name or a different letter or something like that. So I think we're pretty much there. I take over in this domain on the regular video, but I start off with a sample notebook, and I start off with having run the command to get everything started. So let's just see. I used this in class last night, but this particular PowerShell window, but when I first started it, the first thing I had to do was list my environments, see which environment I have that I want to activate. So then down here I activated it, and then I launched Jupyter Lab by typing Jupyter space lab, and then all of this stuff that follows. Was it launching up and opening up a web browser? And then as I run with it more and more and do more things, it just keeps talking to the PowerShell. It's not something you generally look at unless you're debugging, but that is in here. One thing I didn't do last night that I'm going to do quickly before I stop recording and hand over to the regular recording is what I've had to do is go under Settings and go to the Settings Editor. And I always have a hard time remembering where in the Settings Editor I want to go to, because there's so many things in here. It's something that may bother you and may not bother you. It had become an issue for me, and then I found by Googling how I could manage this. It's not Document Manager. If I can't find it, I'm going to try to remember how to find it next week. It's Notebook. Okay, it's Notebook. And down at the bottom of Notebook, you will see something way down in Notebook. It's called Windowing Mode. The default setting for this is full. And when you have a very large notebook with lots of graphics and other things, the notebook starts kind of losing itself, where it can't refresh everything on the screen because there's so many cells in the notebook. So I found various articles on this, and I found that setting it to defer, and it explains what it does. It improves loading time, and it just overall works the best for me. When it says here full is best performance with side effects, I find the side effects very discouraging, so I went with defer. And all you have to do is select that, and then when you close settings, it will now be using that. And you will get notices down here that talk about whether there's upgrades to Jupyter Lab itself, and those can be put on using Conda. Someday in class I'll talk about how you can maintain your packages. So I will not ask for questions because my audience is not here, but I'm going to carry on and start producing this video with this segment I just recorded, and then the big segment that was done last night successfully. So I will sign off. Bye for now. Okay, welcome back to the class. We may have trashed the first part of the video because I didn't have the resolution set properly. This is too new of a podium system. It wasn't going to let me do it automatically. I had to force the hand of my computer. That's the nice thing about using our tools that are web-based, is that they adjust much more readily for size variations than an individual app does. So, okay, so now we got into PowerShell, and what we've got going on here is it says base system, so I can go conda env list, and it's going to list all my environments that I have installed here. And you can see the one that I want in there, so I'm going to go conda, and if you want to know what your options are with conda, -- help should give you, all these different options you can have. But we're going to go conda, and this is in the document we were looking at, conda activate. So I didn't type the name correctly. Oh, I know what it is. I have an underscore in here. No, that's not right either. Let me make sure I know what the name is. DSP-COM313. Okay, I was typing the wrong name all along. Wait a minute. I can't read my own writing. DSP-COM313. Can you see what I'm doing? It's wrong. I guess I didn't have the 313 in there. That's what it is. Okay, see how I make mistakes all the time, but the last line there is telling me, you see the prepending DSP-COM313. So we're in the right environment. So I'm just going to go Control-L to clear it out, and I'll go conda list. And we can see from this massive list of packages, everything that I put on the system last week, or the week before last, all alphabetically listed, but we can see Scikit DSP-COM 2.1, we added that. A lot of these other packages we added to do the Jupyter Notebook, Jupyter Lab, the widgets should be in here, and Pi Audio should be down here. Right there, Pi Audio. I mean, you can just see what the packages are that you installed, and you can also see the version number. So, and you can tell whether it was installed by Conda Forge or Pi Audio was installed by PyPI, which was the pip installer. So we're good to go there. At this point, we could launch Jupyter Lab, and that's what I did over here just before class. I got switched into my environment, just like I took you through. And then once I got in the environment, I just typed Jupyter space lab, and then that brought up Jupyter Lab over here. So then I was good to go. That's the point you want to get to, and then you're in the browser from here on out. I'm not going to use it this instance, but I am going to get to that here maybe just before the break. I just wanted to grind through that, get that behind us. So that'll be the routine that you'll go through every time. Start up your terminal, whether it be PowerShell or the command prompt. Miniconda might install a special version of PowerShell or a special version of command prompt that you run so you can get access to Miniconda. Just take the lead on that. I mean, if you look at your Miniconda install, I guess you can do that here too. I don't remember. I haven't done mini-conda on here for a while, so.
Yeah, add anaconda prompt that you run it in.
Where did you see that? Oh, up at the top?
Oh, no, that's what
Oh, that's what you got. Okay. I've had so many different versions of this. It should be in here somewhere, though. You'll just have to look and see what the options are once it's installed. For me, though, what I did is I just mounted a terminal up here so that I could get access to that as one of my pinned applications. And then the other things that I'm using are up there. Just follow the directions. You can do PowerShell. Does yours say PowerShell also, or just command prompt?
Anaconda prompt.
Okay. But then you can you get to the stuff from there?
Yep.
Okay. Okay. And
Different type of PowerShell, I guess.
yeah. No, they do different things because there's permissions that have to be done in order for it to run, and I've delved into breaking those rules, but I don't want you to get your system all bound up and be upset with it. Just follow the instructions and go to the terminal or PowerShell prompt that will let you get the job done. So generally, once you get there, you'll be able to download one of the notebooks I have on the website, which are all here. So this is the one you want, probably. This is from fall 22-22. I think I have a newer one, but I don't know. I might push up a newer one. I'm not sure. And then chapter 2 is the material. Chapter 2 right now. So we've got, both of these are the notebooks I think that I have opened up right now in the browser over here. As you can tell, if you look at my list that I've got in this folder, they go back 8 years. I mean, I've got just a lot of different things I've whipped out as needed. And if you ever have to start a notebook from scratch on your own, you can do this, and then you can get a launcher. So a launcher for a new notebook would bring up a blank notebook. And generally, I sit there and I'll say, what do I need to get this thing started? I'm going to go find a notebook that I've already created, and I'm going to copy these into it. So I will have a means of getting started. And then when I do Shift-Enter on that, that notebook will run, and you'll see a 1 light up in there. This little circle is filled when it's running, and it's open when it's not running. And if you wanted to add another cell in, I can make that be a markdown cell. And then I can take this cell and push it up above and mark down a single hash like that would be. Shift-Enter. And that comes out of the notebook as the text that goes with it. This is Jupyter right now, yeah. Yeah. And Jupyter has another nice feature to it that's automatic, like here. That's the table of contents, so you can see all the things I have built into this notebook, and I can just click and drive right to that point and get back to where I was working. Or if you're looking at an example notebook I created that has a lot of different problems in it or things from the lecture, and just zoom right to that point and start working with it. You will have to always start at the top, though, and run the opening cells. This sort of kicks everything off. This says load up all of NumPy, load up the graphics. This line here, the % is it's called a magic command for the IPython original creator. And this inline just says put the graphics in the notebook rather than opening up in a separate window. You used MATLAB for a number of years already, and MATLAB always had its graphics in a separate window, right? This works the same way, but I prefer to keep the notebook, the graphics right in the window. And then I'm loading the SIGSYS module from my library, giving it an alias of SS. I'm loading scipy.signal, which is a core set of functions for DSP. I'm calling it just signal. And then I'm loading in some other pieces that aren't always used, but I am using the SVG library and the image library. And then at the very bottom here, that's another magic command. It just says configure the back end so that all the graphics is scalable vector graphics. You want that because that's very sharp looking. It's a vector graphic, whereas if you don't run that line, you'll get a PNG graphic that's grainy looking. The vector graphics are much faster. And now that you got me going on that, I'll just run a line here, a couple lines of code. Here I'm going to say a range of integers going from 0 to 25. I'm going to take a function that's in the library SS, and what functions are in the library SS, dot, tab, and these are all the functions that are in that SS module. There's a lot of functions inside of there.
So you can like type out stuff on this and run Python code?
You can write your own Python code?
You can like type that out?
Yeah, absolutely, absolutely.
Okay.
And I'm going to show you that before the class is over today. And then when you're inside a function, like dstep, shift-tab should bring you up to help. But if it's not working right now, let's see, it's not working for whatever reason. There it is for arange. Arange is just a function to create a range of integers or floats into a NumPy array. I don't know why dstep is not working at the moment, but how do you save yourself from that? If you're ever using my function library, though, you can always go back to course materials, and you can open up the documentation we have for DSP.com, and you would go under the module Signals and Systems, SIGSYS, and then you get this listing on the side of all the functions. We were looking at dstep, so dstep is right here. It gives you some examples of how to use it, and so on. My co-author wrote all this documentation. He was pretty, I mean, to me, this is also very handy because it's gotten so big that I can't remember everything. I did an upgrade about a month ago. I added a bunch of new functions, cleaned some stuff up, and I can't even remember everything I added, but it's stuff I've been using a lot in my work, and I said I'm just going to push it in here to be available. So to you, it should seem like an awesome collection of stuff. And the Signals and Systems for Dummies book got me started, which, how many of you saw that when I passed it around? Was it 2 or all 4 of you?
I think it was 3.
Okay. It's sitting up here. Come and look at it. If you haven't seen it, it's sitting up here. So now that I'm way, way, way sidetracked and we're about ready to take a break, it goes till 5:50, right, the first session? Is that right?
Yeah, I think so.
It's something like that. I don't remember. Or is it?
It's somewhere in, you're pretty close.
We're pretty close to the break time.
Yeah.
Okay. How do we know? How can we figure that out? We're engineers.
When did the class start?
It started at 4:45, but when I made this, I created the office hours link. And in the office hours link down here, how did I do this again? Wait, I still have to finalize this now. I have this. Remember, this was from the first day of class, so 4:45 to 6 is what it goes up to officially, according to the university scheduling. and then 6:05 to 7:20. So remind me that we still have to debate this. You guys, two of you were in here when I came in here, and had been empty, right? Do you think?
It was empty, yeah.
I think I could do the office hours, and here's what I'm thinking, if it's empty.
No, I mean, the class ended, the previous class ended at, 4:20.
Okay, 4:25 is when it could have gone to. So
Okay.
there's a few lounge chairs out here, though, so we could just, I'd like to just be able to meet somewhere where we don't have to go somewhere separate. We can just hang out somewhere nearby.
Yeah. I would not be able to go to office hours beforehand.
Yeah, I remember that. So, and you can walk out this door down here and go right over to the student center too, right?
Yeah.
So I could agree to be in there, I suppose, too, if that was appropriate. Right now, I'm not signing up, but if you gave me a Slack message, I could be over there.
I'd prefer just sending you a Slack message and we can meet up.
Okay.
I think
But we have areas that are really close by here that I think we can do that in. Agreed?
Yep.
We don't have to go running. I mean, I used to work in this building. I used to have an office. I have the lab that I can still go into, but other than that, I really don't have any affinity to being in that room. It's, you know, they're going to start demoing it in another month. They're going to start demoing the wing. The east wing is going to get demoed first. So it's going to be kind of a construction zone inside of there, is what I've been told. Sounds exciting, right? Okay, so I got pretty well sidetracked, but I want to jump back over to this just before we break out of here for our first break. So last week when I was taking us down, we were looking at the unit impulse function right here, and we were also looking at delaying by an arbitrary amount. So anytime we have a sequence and we want to shift it to the right, we put in a minus some positive number. If we want to shift it to the left, we add a positive number. And you can always get at that, you know, the way I always get at that, like for this function down here, if you had when does the delta function turn on? It turns on, according to the definition there, when its argument is equal to 0. So what can I do to just verify that? I would just pull that out of there, set it equal to 0, and then rearrange it. So when n is equal to n naught. I mean, you get to do that anywhere, everywhere, whenever you are questioning in your mind what's really happening. You can just always check that math. And we'll look at that again later. So you can use a delta function to write any linear combination of functional values with this representation. You can just take x of k as if it were just a list of numbers. It's not associated with the independent axes n. It's just a list using index k. But you can locate each of these guys on the axis, like this one is A1 would be like x at 1, and then it's located using x of n minus 1. Now you're saying, that's so silly, why are you doing that? It's redundant. Well, we're going to use this when we use a time-invariant linear system wrapped around both the left and right-hand sides of that. We'll have an operator that operates on x to produce y, and when you operate on that operator on the right side, it will do things that are very convenient when the system is linear and time-invariant. So this little representation, I put it in a blue box because it's like a crutch. I mean, we're thinking outside the box a little bit. We're just going to do something that seems kind of silly. Is that acceptable? You may remember this from before. It's just a game, and mathematics is game playing most of the time, just trying to be very formal about everything. And by the way, as a systems engineer, you get to be the more formal type person in your group, whereas the FPGA implementers that I work with, they're not really fond of thinking formally in math, but I don't know, we spend a lot of time learning math as engineers, and we can benefit from that, I think. We don't have to be like the mathematician professors we learn from, but we can still be more formal mathematically, and I think systems engineers like that in their vocabulary. They like having that as their roots, that they grew up with that.
Would x of 1 show what the magnitude is of that?
Just the value. It could be a real number or a complex number. We'd have to take.
So those a sub n right there, those are basically x n?
Yeah.
A minus 3, that's x of minus 3?
Yes.
Okay.
Absolutely. Yeah. This I was inspired by what the book had written in it. But you can see down below there, it just has expanded out like that. And we'll do that after the break. I'll just go into Python and just show you how you could just have it draw you this picture. You could do it in WX Maxima too, but I'll show it to you in Python. Okay, the unit step sequence is just the next one in this set of definitions. And the unit step sequence just is defined to be 1 whenever n is greater than or equal to 0, and 0 for n less than 0. It's almost identical to the continuous time version, but in the continuous time version, they say it's a function that's 1 for t greater than 0 and 0 for t less than 0, and then they leave nebulous when t is equal to 0. And in analog signals and systems, that's because can a function instantaneously jump from one value to another? Can it really do that in physical terms? It can't. There's always parasitic capacitance and inductance that's going to keep it. It just can't change like that. The mathematics, though, lets you do that, and that's where the math and the physics kind of wrestle with each other. DSP doesn't have that problem, though. DSP is a sequence of numbers, and it changes as another value at each integer, which is stored in an array on the computer, typically. So it's not a problem. It's cool, is what it is, because it's just so it's in your face. It's like, it's this. It's not anything else like it is in the analog world. So as a matter of fact, we can take that sequence and we can write it in this form here, which says, how would you visualize that? And the way I would visualize that is I would say, take this k-axis and that's delta of k sitting right there because it's sitting at 0. So now think about this sum is scanning from minus infinity up to n. So we're going to start summing at some point. If we start summing over here, if that's the value of n right here, what happens when we sum from minus infinity up to n, we're going to sum up all the values on the axis k there, and we're going to pass through, and we're going to grab on to x delta of k. So that means, what do we get out of that sum? 1 or 0? It's included in the sum, right? The green line down below is scanning up or summing up from minus infinity up to n. It captures the delta of k. If, on the other hand, the delta of k, the n, was back over here, we would not capture the delta of k. So it plays out properly that this, writing it as the sum of delta of k with these limits, makes this indeed behave like a step function. Because as long as n is less than 0, it can never capture the delta. And as long as it's greater than or equal to 0, it always captures it. So it does behave as a step. Likewise, if we turn the axes around, we can see that by changing the variables in the sum, we can have it be a sum from k is equal to 0 to infinity of delta of n minus k. Now, I can sketch that out, but I could also say you should go do this on your own on a sheet of paper and just prove to yourself that you can visualize how that works. Does that sound reasonable? I realize when we leave here tonight, unlike on the morning time slot, we're going to feel tired, and I'm going to feel tired, I know that, but you still got to keep thinking about this stuff, and I'm going to go through problems in the second half of the session too. One of the things is you got to tackle problems by starting to work on them and then set them aside, go to another one, and just get started and kind of get yourself kind of in the driver's seat. I got to feel like I'm kind of figuring out what I have to do. Don't leave a problem to the very end, like an hour before it's due. Get a look at them so you can kind of get them loaded in your brain and start thinking about them. Because almost always on the homework problems, there are some problems that are just bending your mind badly. You know, you don't see it right away, so you have to look at it, you have to set it aside, come back to it. But what I want you to do is find problems that you can work right away and say, that's easy, that follows something in the notes or in the book or whatever. Get those done, and then get a look at those harder problems and say, I'm going to think, but I'm not going to think too long because I want to get something done, but I'll come back to those. And maybe you'll be thinking about one problem before you go to bed, and you'll wake up in the morning taking your shower or whatever you do in the morning, and all of a sudden, bam, something will hit you like, I can try that and do it. I mean, you can't try it when you're in the shower, but as soon as you get out of the shower, you might want to sit down and say, wait a minute, I had all this stuff scribbled on my paper. I think I now know what I can do. You've done that before, right?
Yeah.
So you just got to get that clicking for this subject, and it should work for you. I realize you get desperate. You can Slack message me too, but it's, I don't know, it's exciting to learn, right?
So for the unit step, that's continuous, right? It just goes up and it's continuous.
Yeah, but there's still dots. It's still a stem function. Yeah. You have to get that lodged in your brain. So this is what the step looks like. It looks like that.
Yeah, because like in previous classes, somebody just draw like a line, and it's like continuous, but...
The continuous can do that.
Yeah, okay.
And that's what this U of t does, but it doesn't get defined at t is equal to 0. So it's not hokey, it's just that we have what I call, and what I learned about in school when I took math classes, it's called operational math, an operational concept of math that is very convenient for engineers, but the fine points of it kind of break down when we have a 0 rise time step function. You'd say, I can go to the oscilloscope and turn the time-based knob on the oscilloscope and zoom way in, and what are you going to see when you do that? You're going to see that it actually rises up with some rise time, right?
Yeah.
DSP, not so. It's going to just step like that. So I won't go through these, but you can look at those similarly for the continuous time delta. And we know that if you differentiate a step in an operational sense, you get a delta function. That requires some convincing, but as engineers, we've been convinced of that enough. Mathematicians stumble with it probably more than we do because we take an operational view on the derivative of a step as a delta. So what does it mean to have the difference on a step function? Well, it's got the name first backwards difference. So a delta sequence can be obtained by subtracting a step or subtracting a step delayed by one sample from the regular step, and that isolates then in that subtraction the single spike sitting there. Remind me to show you that in Python, because Python does that with a single function command called diff, or diff, which MATLAB also had that exact same named function, diff. When we come back from break, we'll be looking at something that seems innocuous, like an exponential sequence. How can that be so hard? But you've learned about continuous time signals so much of your life as an electrical engineer that this is a little bit harder to accept. This is like the first brain warping challenge, the way I think of it, in teaching this subject, when this happens. Okay, I'm going to pause, and I'm going to attempt to see, can I pause? That recording, we were looking on the website where all the course notes are, so they're right here. You can be looking at them on your tablet. You can use it however you want to use it. So we're going to go back over here. We're going to look at the sinusoid, and I'll probably do something with this in Python. So this exponential sequence is in the book in this exact way. It says you form a signal that is A times alpha to the n. And A can be real or complex, and alpha can be real or complex. And there's no limit on the axes n. The axes can run from minus to plus infinity. We could later change it with a unit step function to start at n is equal to 0, or any of those things. But this is getting you into the idea of a discrete time sinusoid. So, because sinusoids, as you first learn about them, start at minus infinity and go up to plus infinity. They're just sort of a signal that's been around been running for a long time. So, as a first example, though, we can use alpha to control whether the sequence is increasing or decreasing. So we make alpha greater than 1, and it will be expanding, exponential. We make it less than 1, and it will be decreasing, between 0 and 1. If we make it less than 0, then it will be alternating. And then in the second statements here, it says, suppose A is just a magnitude in a complex phase. This is like a phasor from circuit theory. And then we're going to make alpha be a complex phasor too, but we're going to use different terms here. We're going to say the magnitude of alpha is the exponential decay factor magnitude, and then it has a e to the j omega naught, which controls the frequency of the oscillation. So now we can create a sinusoid that's complex, has sine and cosine components, that is either growing or decaying, and we can mess around with that by just controlling what we do for the magnitude of alpha. So with that, we can create this form, which is probably our most preferred form in digital signal processing, because we generally think of complex exponentials or sinusoids as being a valid signal. I realize in the lab you don't think of it that way because you only think of a sine or a cosine, but in a communication signal scenario that we deal with in DSP, it's a complex sinusoid is very, very real. It happens all the time, as a matter of fact. But Euler's identity lets you expand it into cosine and sine, and then you can make it be as simple as just an exponential that is 0.9 to the n. So that's a real exponential sequence. Generally, though, when we think of this sequence, more often than not, if we think of it, we won't have that here. We'll just have zeros in here. And so we'll make it be (0.9 to the n times u of n. So it starts at n is equal to 0. Why don't I like what's on the left? What bothers you about the sequence on the left?
It just starts at minus infinity.
Yeah, it's going up towards infinity, and doesn't that bother you?
Of course.
Yeah.
You can't go back.
Because infinity is a concept.
Yeah, so it just shows you the mathematics of it, though. And in DSP, you can flip things around a lot more freely than you can in continuous time, because it's just a series of numbers on the computer. You can play all kinds of crazy games with them. You can actually make time go backwards by just starting at your array and accessing it in reverse. Or if you're thinking about processing an image, which would be a two-dimensional array of pixel values, you can do interesting filtering things that are called non-causal operations in a single time axis of processing. We get the sinusoidal sequence by just taking the real part or just thinking of the cosine component. And this is a nice looking signal, A cosine omega naught n plus phi. So we can interpret omega naught as radians per sample, even though samples don't really have a unit associated with them. But it's just more convenient to think of it that way, because then you can think of radians per sample times the index n as giving you omega naught in radians. So the samples cancel out. Then you can have the complex version of this, but let's just for a moment study the real version, and then that brings up the concept of continuous time sinusoids are always periodic. You learn that at a young age, and you just think a sinusoid is always periodic. But now what about a sinusoidal sequence? Well, the concept of periodicity in a sinusoidal sequence is that, it's what's in the blue box down here, that you can take the sequence and pick it up and move it over by n, one way or the other, or multiple iterations of n, and then it will repeat again. It looks identical. So this is a little bit mind-boggling, because not all sinusoidal sequences are periodic. Is that believable? I mean, it's something you have to just confront and say it's true. But if we have, it's really convenient to think about how can you even have a periodic sinusoidal sequence. You have to have property hold, and that property is talked about here. How do we get a periodic sinusoidal sequence? We would say, what value of n can we throw in over here that makes this equality hold? Well, cosine is a mod 2 pi function, so it must be that omega naught n is some multiple of 2 pi. Then we know we've created a periodic sequence, and if we rearrange that to solve for omega naught, we see that in order for it to be periodic, the frequency has to have this rational number k over n times 2 pi. So the only way to make a periodic cosine sequence is it has to be a rational number k over n times 2 pi. So if you picked n, the period, then you only have a finite number of options for making unique periodic sequences, because you'll eventually start over again. Once you let n run from, say, 0 up to n minus 1, as soon as you try to create a higher frequency, now you'll be able to cancel out a factor of 2 pi and you're back where you started from. Is that okay? It is the reality. And these unique frequencies form what are used in the fast Fourier transform or the discrete Fourier transform later in the course. So they're all there well and fine. So we have this property that they're indistinguishable. If you take omega naught and add some r times 2 pi, where r is an integer, you're just going to get what's called an indistinguishable frequency. So the distinguishable frequencies are just these n right here. This actually couples in with sampling theory, which won't be talked about till chapter 4, so I don't really want to get too far off the deep end, but just thinking about this, it's useful to just be thinking that this is true stuff and it's different from the continuous time. I think what I tried to say the very first day of class last week was there's a lot of similarities in signals and systems between continuous and discrete, but there's certain things that just break. They don't work the same way, and this is one of them. A continuous time sinusoid, like I'm just thinking of the function generator in the lab, or maybe me playing a note on my trombone or something. It's a periodic signal. It's just the nature of it. I mean, as long as My embouchure can produce a steady tone, it's periodic, but a function generator, you trust it to produce a nice periodic signal. A sequence in the discrete time domain is not always periodic. As a matter of fact, if you start with this example, if you set omega naught equal to 0 or omega naught equal to 2 pi, you just get a constant value like this. If you set omega naught, say, equal to pi, and the printing here is messed up, it should be that, pi over 8, and 15 pi over 8, they're identical. Now, if that seems amazing, for a cosine sequence, what it is we've got pi over 8 and 15 pi over 8 are just a 2 pi shift. So we come back around again on our unique signals. This is tied in with aliasing and sampling theory, which we'll be revisiting in Chapter 4, but which you've already seen. You learned about that in 2610. And then here's just another example. Here, the notes didn't come out right, or maybe this program isn't rendering properly, but pi over 4 and 7 pi over 4. So you can just factor that out. And the way, if you were needing to fumble with this, you would say, I can pull out of that right, and then if I look at this, that's 2 pi, so we know when we shift the frequency by a multiple of 2 pi, it will get us back the same periodic sinusoidal sequence. So now you look at this and you say, but there's a minus sign in there, but cosine is an even function, so cosine of pi over 4 and cosine of minus pi over 4 are the same. If it was a sine, though, then it wouldn't work that way. Then it would be unique, but we'd say it's the same frequency. If we were listening to that pitch, it would not sound any different to our ears. It would just be out of phase by 180 degrees, but I'm not sure we could discern that or not on a single pitch. If we were listening to multiple tones, then we would. So before we look at systems, let's just go play in Python for a little bit of time here. So just remember, this is the icon for Jupyter, so that's the tab we want to be into. So here I created something from the library, and I just created I get nothing. So why did I get nothing? It's because I didn't let it plot anything. So if I wanted to see what x was, at this point I could not have it set equal to anything, and it will list it out. So we just see we get a bunch of ones, but suppose I started this at minus 10, then ran that cell again. Now what we're getting makes sense, right? It's a sequence of numbers, and we started the index into our step function at minus 10, so put out 0 until it reached the end. If we really wanted to get a better flavor of that, though, what we could do is we could just type the stem function and give it the proper x-axis and put in the x in here, and then we get, the picture that we were expecting to see. And I definitely say you should play like this. Just do stuff, make pictures. I mean, I don't know about you, but for me, pictures makes me learn stuff better or faster. Have it draw me a picture. So what did I do here? I had a step, and here I just said, what is this going to be? This is going to be some sort of an infinite ramp if I was to plot it. It's actually probably not what I was looking for, but I could do this, and I can multiply it times x if I wanted to, or I could just go d step of n. And I could just try to do this, n and y together. Oops. Okay, why didn't that work? Step is not in NumPy or in PyPlot, but it is in this library, SIGSys. So in order to get access to step, I have to do like I did up here. I have to prefix it by the library that it's in. And this is a concept that comes from C++, actually, or at least for me, comes from C++. It's called a namespace. So namespaces allow you to have functions, core functions that have the same name elsewhere in your memory space. And the only way you can keep them straight is to say, I want to get dstep that's in SS, and suppose there was a dstep somewhere else. You would keep them isolated from each other and not overlapping. MATLAB did something that was horrible that I later learned when I got into programming. MATLAB had a list that you would say, where does it first search for a function? If I called dstep, it would give it a list of where it would search first to try to find the function. So it would mask over the other instance of a function of the same name. And that was, in my view now, that's awful to do that. And I found out the hard way. I wrote a library for DSP in this class many years ago, and I picked a name for a function that was also in another library that MATLAB had. And students were saying, I can't get this problem work because my function doesn't work. It gives me something totally different. And then I realized they were getting access to a function of the same name that did something totally different from what mine did. Python makes sure you can't do that by having the namespace. If you don't use the namespace, like I did here, I imported all of the functions in NumPy and all the functions in PyPlot for plotting. They all are now in my single global namespace, and if they're conflicting with one another, I'm doing something bad. So most people wouldn't do what I'm doing, but I'm doing it here because I want you to not have to put the prefix on everything. It gets to be tiring after a while. For me, it does. So when I first learned Python, I just said, I love NumPy. I want everything all there at my fingertips without saying NP. If you read other people's code, they will import NumPy as NP as a shorthand, and then you have to remember to put a prefix of NP dot for everything. I like not making it so intense, but that's just me. Most of my students, graduate students and other people, do it formally. And if I'm delivering code to somebody, I have to do that too. But when I'm running in the notebook, I like to be a little bit more expedient at times and not have to do as much typing, because right now I'm a really awful typer, but I've been an awful typer all my life because I don't touch type. I have to kind of hunt and peck a little bit, and this is making it harder for me. It's actually making it painful if I try to use this hand. But by the way, I am in a lot less pain than I was a week ago, but it's still just doing this, and it gets painful in a hurry, but it's getting better. I'm pretty happy with that. So what else can I do here that might be interesting? So here I just have to put the D step in front of that, and then you see that I have two steps, one that's turning on as a step at 0 and the other one that's a ramp starting at 0 and n+1 ramp. I generally don't like putting two stem function plots on the same graph window because they come up in the same color. There's a way of giving them different colors, but I actually just like having one waveform of stem function plots. So here's a neat little trick in code editors in general. If you hold down the control key and then hit the backslash key, you can comment and uncomment code like that very easily. If you've never learned this before, start using it, because it'll make it really easy. You write a bunch of code, you think you got it right, and now you're getting all these error messages. So what I'll do is I'll start commenting lines of code out until it starts working, and then I figure out what did I do wrong, because typically you don't see your errors right away. You're in a hurry and you're typing away, and then you go bang, like run all these lines of code in a cell, you get an error and you're like, you gotta go search for it. But the commenting idea is very popular in me. Like in this notebook over here, I did a kind of a nice little example where I said, let's create the difference between two step functions, a step function that starts at n and a step function that starts at n starts at n equal 1. So we see the difference, the first backwards difference produces what we were expecting to get. We get a delta. Whereas here I just used the D impulse, so if I want to just prove it's identical, I'll just comment that line out, uncomment that line, and run it again, and I get the same thing. Now, based on something I told you a little while ago before the break, I said we have another kind of nice function in here, so let's just create st for step and say it is ss.dstep n, oops, stupid, there's Velcro on this, and I move around and the Velcro catches, so it moved my hand, it got caught on my shirt, which I'm not fond of, but it happened. I wanted this line down in here. And a lot of times if I'm typing from my own library, I will type the dot, and then I will type, I'll get that long list, so if I type one letter, like D, suppose I back up here and do this again, D, now I just have the D's, right? I'm homed in on it, and if I don't remember what it was called, I said, oh, there it is. That's what I was looking for. And I'm just going to put in N. And then what I'm going to do down here is I'm going to do this. So I'm going to use the diff function, which does this backwards difference automatically. If I go Shift-Tab on this, it should give me the help for it, but it's not. This is a NumPy function. I'm not sure why the help isn't working for me, but let's just see what it does. Don't want that line. Instead, I'm going to plot my fingers. This keyboard has got very tightly spaced keys, unlike any other keyboard I own, so my ability to work with it is poor because I'm used to my other keyboard. Anybody ever had that problem if you work on more than one computer? Your fingers get good at one keyboard, and as soon as the keys move just a little bit, all of a sudden you're doing all kinds of bad things that you don't want to do. And the mouse is very sensitive here too. So what I wanted to do was put in the diff in here, which is delta. So I type two letters, I can hit tab, and it's already started to learn a little bit about it. It says like, okay, there's a value that you've already typed before. It's in your space of names, so you can use a lot of shortcutting things. So we'll do that. And I did this on purpose. Like one little mistake, and look at all this stuff. I just want to teach you something about debugging, because Python can spit out all kinds of junk like this, and it's irritating, right? It's like, what do I do with this? I don't even know where to begin. Do I look at the top? Do I look at the bottom? So in Python, with all these things that it got angry about, look at the bottom. Could not broadcast input array of shape 14 into shape 15. So what does that mean? Well, in simple terms, what it's telling me up here is that after I took the delta, or the diff of ST, I subtracted from the original sequence, I extracted all the values in the sequence shifted to the right by 1. So when I did that subtraction, when I got to the end of that subtraction of those two arrays, there wasn't a value up above that it could subtract from because it was shifted. So what Python diff function does, it shortens the array by one sample. So it made that sample contain one less than what the index n does. So what we have to do is we have to say, we have to modify this with our colon operator and say, we're going to go to I think this will work. I'm not positive I remember this correctly. The colon operator is similar to what you learned in MATLAB, but in Python it works a little bit differently. But it says that I don't have anything to the left of the colon, so it says just start from where the array starts, and then it goes all the way to the end, but I don't want it to go all the way to the end. If I was to do this and say just colon the whole argument there, it would just pick the whole array. Does that make sense? It would just sweep everything in it. What I want it to do is go to one less than the end, and in MATLAB it would have been end minus 1, because remember in MATLAB end is the end of the array, the maximum length. In Python it does it differently. So minus 1 says I'm going to go 1 back from the end. Minus 1 means pull me back 1 from the end. And there it is, but the diff isn't quite lined up right, at least index-wise, because it's at minus 1 rather than at 0. And that's just because of the way I set this up. I didn't do the best job of it. But I could play games with this. I could have this start at 1, and then I could let this just run to the end. And now it's fixed. It looks better, at least. There's all kinds of things you can do with Python that you get very adept at doing. And if you ever want to get the length of the array, it's rather than writing out the word length, it's just len for length. So what is the length of n? We've been seeing it's 15. I can just get a whole list of lengths in here. I can get the length of st, and we can see what the heart of our problem was. Delta was hosed up because of the diff operator. So it just gives a tuple of 3 values. Tuples are talked about in my Python basics, but n and length st are both 15 because st was derived from the array n. But delta, because of the way it did the diffing, it gets 1 less, and that's 15 and 14 was what was hosing up our calculation. Make sense? I'm sorry, but you have to experience these things. You have to have a little bit of pain with any coding language, right? MATLAB dinged at you whenever you made a mistake. And I used to hate that dinging sound. It's like, make this work. Python doesn't necessarily ding at you, but it gives you all this pink stuff that we saw down below here that you have to clear out. And I know in working homework problems that becomes frustrating because people have turned stuff into me for homework saying they just, at the 11th hour, they just couldn't get it done. They had a mistake and they included in their homework paper all this pink stuff saying, I just couldn't figure out what this was. So the first tip of the day is look to the bottom of all that pink stuff, and your chances are you're going to see something that's going to be a clue as to what you did wrong. The next thing you might do is if you just can't see it, you might comment out a line that you think is suspicious and see if the code runs without that or something similar to that. I said I would do some plotting with sinusoids in here. So this one looks like it plots. We can just create a new blank space in here. I can say n is equal to a range. Let's make it be longer. So a range, I didn't set a start value or an end value. So what Python is going to do it's going to give me integers going from 0 to 49. Python is a zero index based language like C is. MATLAB was a ones based language. They're different. Julia is a one based language. WX Maxima is a one based language too. Personally, I like zero based better because a lot of real serious coding is done in C and C++, but mathematicians have arguments and other engineers have arguments too. We can't change it though. It is what it is, so you'll just have to get used to that index starting at 0. But what Python NumPy does, the arange function always will create the number of elements equal to what's in there, so 0 to 1 less than the number. If it was MATLAB, you were creating something, you would have got 50, but they would have started at 1 and gone up to 50. So you just have to get used to the idea that it's shifted back. So there's that. Then we're gonna go sine 1 is cosine of 2 times pi. What value do we want to pick? We'll pick pi over 8, let's say. I'm not sure I wanted to do it this way. What I really wanted to do was make it align with the notes better. So let's pick one example from here. We had pi over 4 and 7 pi over 4, or how about pi over 8 and 15 pi over 8? That probably would have been better, so I'll just change that. And then what we have to do is get a plot going here, so we'll do a plot. Stem of n, S1, all right, where did it go? They're identical. We're not seeing any difference. It's not really too exciting at this point. I'm going to cheat a little bit. Once you've done enough stem plots and stem is not being either requested by the homework or you just want to get a better feel because you're plotting more points, stems get to be too much. They're too intense to have all those vertical lines in there. So let's just change it to plot. And now the points are overlaid, so we don't see any difference. If I was to put a phase shift in here, say, pi over 3, we're going to shift the phase of one of them. We can see that, yes, they are, they do have the same period. The phase shift just shifted one with the other. It's either a phase shift or a time delay because they're equivalent for a single sinusoid. And we could have done that with a stem too. This is where stem is just gets more confusing. You just have to understand though that that is not too helpful because it just looks, you'd have to have them in different colors to see what's going on. But when you have it, the dots connected, you just can't get hung up on the values actually being there because they're not in our sequence. Okay, time is ticking, so I'm going to leave this for now. Is there anything that you want to see in MATLAB right now?
So is this in, like on the website, like the base code? Because you have all those import.
Yeah, it's on there. You want that. Yeah, you want the base code. You want to make sure
Yeah.
you can get this. And I have PDF renderings of these too. So if I'm in a hurry and I need to get something, I might go to here and
Copy and paste.
I can copy and paste it from here. That works too, most of the time. You get zing sometimes if there's a character in here that PDF doesn't copy correctly. Python will figure it out because when you run that cell, it'll give you an error message. So you just got to be kind of on the lookout for that. Okay, we want to look at systems. We want to be able to get to the point where you can work homework problem number 1 and some other stuff along with it. And then we've got a half an hour left right now too, so time is really ticking down fast. I also want to show you types a little bit too, so that you can put things together in your solutions. So discrete time system, the generic operator is T. It's just something that operates on the input sequence to produce a corresponding output sequence. T doesn't mean it's linear. The book later changes to L if it's a linear time invariant system, but T is just some remapping of the input points to the output points. Simple example is the moving average. This is a favorite in signal processing. It's a favorite, I think, in the stock market economics or something. They say this stock is, it's been doing this well because we've averaged it over so many months and we've seen it has a nice trend to it. So the moving average, if you plot it on the timeline here, what it's doing, it's taking M1 feature values, and it's taking M1 past values, and it's taking, I'm saying this backwards. It's taking, when K is positive, we're taking past values, M2 past values, and then these are future values because of the minus sign. They're actually coming from the other side of the timeline. They're coming from out over here. So I need to say that. That's past. So usually M1 is equal to 0 because we don't have the ability to implement a non-causal system. A non-causal system would try to take feature values of the input and use them to form the output. We can't do that in real time. If we had stored values, we could do that. Our analog circuits definitely can't do that. They can't look ahead in time. It's possible in discrete time if you have values stored, but if you have values stored, you're never really looking ahead. So, but it's averaging. So the idea of the averaging is we're taking all the black dots there in this causal version where M2 is equal to 5 and M1 is equal to 0. We're taking the present value and 4 samples in the past and forming an average based on that. Does that make sense? We're also getting some of the definitions worked in here. So causality means that the output only depends on present and past inputs. If it tries to look at a value into the future, it's non-causal. And that gets asked in some of the homework problems. Memoryless is a special case of causal. Memoryless means that it doesn't use anything except the present. We can't do a whole lot with memoryless systems. We can have a nonlinearity, like a power series, which is what's down below here, a power series nonlinearity, but we're only using the present value of the input. We don't really get a lot out of that. It is used in practical applications. So if we're trying to calculate power, we might square the signal or energy, sum the square it and sum it. So that's, we've seen causal, memoryless. Now we're going to look at linear. If we got off of this example right away, and we got off this example because in my notes, that gray bar just means that example was ended. So now we're just back into the regular routine, and we're going through the definition. So linearity means superposition holds, which means a linear combination. The input can be sent through the system to give an output, or we could send the individual inputs through the system one at a time and then gain scale them accordingly to form the output. To me, kind of a classic example, and I use this in the Dummies book, I was thinking of the karaoke machine. What does the karaoke machine do? There's music that was pre-recorded that plays, and then the singer comes up with a microphone and they sing into the microphone, and the two things are playing out together. That is the ideal linear system. If the singer gets too excited and sings really loudly, they'll distort the amplifier because they'll overdrive it, and then the system is no longer linear, so the output is not the sum of the two inputs with some scale factor. It'll be a distorted version of it. Maybe that doesn't make sense because you've never done karaoke. I don't do it either, but I was at a birthday party for somebody, an older person, and it was at a bar. This was my wife's family up in Denver and Greeley, and he sang New York, New York to karaoke, and he had a blast doing it. Supposedly it's his favorite song to sing karaoke in a bar, so he got to have his dream come true. He got to sing it in front of all his family and friends. He enjoyed it, I could tell. I think he may have distorted minimally because the karaoke machine was pretty good and let him get really loud. Okay, so generalization, we can take any number of inputs and do that same linear combination in place of the output. So that's linearity. So now we've got three definitions down. We had causality, memoryless, and linear. The next definition is time or shift invariant, and this one is easy to remember because it says the system has no time varying components onto itself. It can do linear operations, it can do causal or non-causal, but it doesn't change with time. And I always think of this as being, from an electronic standpoint, it's like a built-in amplifier. It can amplify a signal. If I amplified the signal, I input it today or tonight or tomorrow morning, it will amplify it in the same way. It will be delayed in time, but it doesn't get changed in how much amplification it receives. In analog electronics, it's hard to make something that's time invariant because components age with time. They might work differently at night when it's cold, differently when it's hot outside, but a DSP system, you have to purposefully put something into the algorithm to make it be time varying. An adaptive filter is an example where you want it to be time varying, and we can do that. We can make it adapt over time, and we'll destroy its time invariance property, but we'll get some desirable property like an adaptive noise canceling. Does everybody have adaptive something like earbuds or something? They're amazing, right? They work, I think they work really, really well. Not perfect, but they work well. So that's time invariance. We've already talked about causality. This is the formal definition. It was just mentioned up here as a type of system, but the formal definition is here. And the fifth one is bounded input, bounded output stable. That just says that the output will be bounded for a bounded input if it's a bounded input, bounded output stable system. So there's nothing you can put into a system that's bounded that will cause it to go unbounded if it's stable. On the other hand, if it's unstable, then you can hit a resonant point, say, in a system, and it will blow up. I mean, the classical mechanical engineering example is the Tacoma Narrows Bridge, which I remember seeing probably in physics or something. It's where the wind shear came along, the bridge started oscillating, and something in the wind currents were resonant with the bridge, and the canyon that it's in, and it started oscillating, and it grew and it self-destructed. We can build systems like that in DSP as rarely as you can in analog. We can go unstable. So the best way to test for it right now, without linearity and time invariance being given, is just testing with an input and say the input is less than bx, which is less than infinity, and then we have to show that there's a by that will correspond to the output for it to be bounded input, bounded output stable. So we're going to get to the most common form of using a test for bounded input, bounded output, and that's when we have an LTI system and you have one set of homework problems that use this exclusively, and it's a piece of cake to go through and test it out. You want to find those problems and do them. So what is linear and time invariant? That's where the system is both linear and time invariant, and then it has extra nice qualities to it. It happens to be our most common type of system that we study in this class. We have linear and time invariant systems. They can be characterized by a system impulse response, which is like the signature of the system. It's the same today as it is tomorrow. It doesn't change with time, but it characterizes the system. So the impulse response is just firing in a delta when the system's at rest and getting its output. That characterizes this guy right here. And that's in homework problems, obviously, too. So we go back to what we looked at a little bit earlier tonight. We can write x of n as a linear combination of time-shifted delta functions. Now we plug that definition in. It's sitting right inside here. And then we're going to operate on it here, and we're going to say that is y. That's the output. And if our system is linear and time invariant, the linearity part says what? It says that we can take t, we can move it inside the sum operation because we can operate individually on each component, and we know that if it's linear system, it will not change the output in any way. And because it's linear, we also know that gain coefficients out in front can be moved outside of the t operator too, because they just ride along and are transparent to the system. So that's x of k in this case. So when we take that into account, we know that this t operating on that delta will just be the time-shifted impulse response. And when we make that replacement, then we get these two results. Depending upon which change of variables we're using, we get the convolution formula that says x convolved with the impulse response, or impulse response convolved with the input, is this convolution sum. And this is kind of the first cranking type formula that we have in the notes, how we can get an output from an input by cranking through the convolution sum. We will have another way that's more common and more typical in a real system, and that will be a difference equation, and that's, we're a little ways away from that yet, but we'll eventually get to this form. I wanted to get to it today. I'm not sure I'm going to get to it, but I'll just dial to it so I can get to it. More properties. More properties. I forgot how long it was. Way up here. This is the difference equation. This is probably one of the biggest things for the whole course and the whole work area of doing DSP. I mean, this is that type of stuff I'm dealing with all the time in the work I'm doing. This just says there's a relationship between the input and the output, and it's controlled by coefficients. But as a practical means, what it really comes down to is the moving average filter we looked at is a difference equation, and we can look at other operations. What we do with the difference equation is, see if I can find an example in here, we rearrange the difference equation. So we have the output in terms of past and present values of the input and past values of the output. So really what we're doing is we're just going up here and we're rearranging it. We're putting everything from this side onto this side except, let's see, I can write this out. We're going to say that A sub 0 equals 1, and if that's the case, then y of n equals everything, minus sign thrown in here. So it'll be past values of the output minus past values of the output plus present values of the input. So this would become a plus sign. And that's extremely useful. I've got to keep moving now, but this example right here is somewhat intriguing to me. I'm going to just look at this really quickly, even though this is more of the problem set number 2 type problems that you've got on your plate, but there's a little bit in the final problem that's more of just a cranking the answers out. If we had a system which is called an accumulator just keeps accumulating past values of the input up to the present. So you look at this system and you say the output, we're going to just take the very first value that came in and back up minus infinity and add all the intervening values all the way up to the present and form the output. Sounds like a nice statement, but it seems burdensome, right? You have to keep, every time you want to crank a new value of the output out, you have to go back and add everything since the very beginning. So what happens if we do a backwards difference? We do a backwards difference on y of n, we get y of n minus 1. We saw the backwards difference before. What happens if we do a backwards difference on the output? We have this sum that we now subtract from it, running from minus infinity up to n minus 1. So what really is happening there, the only thing that survives on this side is the present value. And we just rearrange it now and say, okay, an accumulator is equivalent to y of n equaling its past value plus its present input value. And when we start the system in motion, we have an initial state, the initial condition, say the initial value here would be, if we started at n is equal to 0, that would be the initial value, n of y at minus 1. And now we just start moving forward from n is equal to 0. And you've seen this in circuits, right? The voltage on a capacitor is initially at some non-zero value. Current through an inductor is at some non-zero value. So it's same idea, it's just a discrete time version of the same thing. It seems, it should hit you like, wow, that's really, really nice. I don't have to do anything with an infinity in it, because we mentioned before, infinity is just a concept, and so it works out nicely. More of that comes down here. It's not the focus of what I need to get looking at for homework, so I'm going to back up over here. And I want to get back over to the convolution problem, but before I do that, I'm going to just show you something in types, just since we are going to run out of time. And I want to show you that in my types example that I put on the website, I've actually got some homework problems worked. There are other problems in the book that are right next to the ones I've assigned to you. So in my types example, you'll actually see some things that might be useful just in working problems. So we went over in here. I opened up types a while ago, and where is it in the website? It's now down here, preparing homework in types. So I give you two documents. One is the PDF output of the document that was saved from the environment where we're going to look at them here in a second. And the other one is a zip package, which has all the files that are inside the types document. So if you create a types account of your own, you would download the zip, and then you would unpack it, and then you would drag them into the types environment, and you could use them, and they would be sitting in your environment just like we have right over here. So over here we have the environment where I have a bunch of figures. I have a TYP document, which is where you do your authoring, and then I have a template document that I just hacked together from reading a bunch of materials. I mean, I built it up over many months of just playing with it, but it just sits there and is useful for you. So there's a lot of boilerplate in the document itself. So most of it is boilerplate, as a matter of fact. I have a bunch of things in here which I don't really need, but I left in here. They don't cost you anything. They just let you do some other cool stuff, but not in this document. Most of them aren't really even being used, but things you have to do in this document, you would put in your own title, you would put in your own name, and you would put in your own date. So that's just customizes it to you, and that controls this. So if I, not my name, but since we have Luke in here, your name is not Wickert, but I just put your name in place of mine, and see it changed on the right-hand side. So, and I could change the date to be whatever the due date is. I don't know if it's the 11th, but it changed. And this ends up being not in this, for my computer. I don't know why it's not working right now, but this is actually a hot linkable, so it's going to be a link when the document's done. More boilerplate, so the document really just starts in here. I wanted to write a piece here, so I can actually just click there. So yours might be, your first document is text problem, something else. Let's see. Custom problem. And you might write it out, you might screenshot it and put it in. But what you can do, like I did here, all of this stuff, I can't make this sit still, all this stuff right in here was actually a cut and paste. It was a PNG file that I scanned from another document, and it's imported right here. It's imported as text _2 -15 _statement.png, and it's sitting right over in here. There it is. That was just the figure that was in there, but now it's placed in this document, so I can use it later. But it could be scan document, like here. Something I did last night, doesn't look pretty, but I did it on engineering paper. Then I took a picture of it with my phone, and I cropped it, cleaned it up a little bit, and it shows up in here. So it shows up, you know, more pages down. If I go look over here, it will be down further. So there's a combination. A lot of things were imported. Cross-references are just so you can cross-reference in your document, but not necessary. And really important thing, though, is put one of these in it anywhere you want to have a page break. So that way you can follow my rule of saying start new problem on a new page. So that's kind of nice. You could just mimic things I have in here. I have math worked out, but you don't have to do math at all. If you just want to assemble it from a bunch of graphics, I think it can work, and you can do more or less as you move along if you want to consider it. But don't sweat about it. Go to Word, something you're familiar with. Don't, just explore just a little bit. Don't get all cranky about it. It's got really nice help online for all of the syntax that you see in here, but you don't really have to use it. I put some figures in that came from It really likes SVG graphics. So if you're working in Python, this came from Maxima, or one of these came from Maxima, and this came from Maxima. But if you're working in a Jupyter notebook, just go back over to look at that for a second. So over here, I'm going to put this right to here. So this is a big long list of stuff, but let's just take this example right here, and there's a function in here, save fig, and save fig lets you save figures. So you can save SVG graphics, which Types likes a lot. It doesn't like PDFs, but it likes SVG and PNGs. It's going to have PDFs eventually, but right now it doesn't. So I would type the name, my impulse, and as long as I give it a name that it likes, single tick mark, I don't have to do anything other than that. So now when I run this, I've already run all the commands above, and what did save figure do? I'm going to look down here, and there it is. See, it popped in there. And if I double click on it, it will open up in Jupyter, but now this file could be dragged into your types document, and there it is. And if you wanted to put your code in here, I could do that, Control C, and then I would go over to types and make a cell in here. I'm going to put it at the end. I'm going to put it in my appendix, just so it's more obvious. Let's see, some back ticks, tell it that it's Python code. My keyboard's giving me some fits right now. Enter is making me backspace, so let's just do this. Control V, my code is in there, and my code should be in the appendix at the end. There it is, but it thinks it's just text, so if I type the word Python next to it, it colorized it with Python colorization, so kind of handy like that. So some things can be documented easily, some things maybe you'll use graphics, PNGs for. I just blew my time window. We're almost out of time, but you guys seem interested in it, so I figured I'd give you something to think about. Engineers, we like to do things neatly, right? So this gives you an opportunity to kind of think about something you could do, but don't, keep your eyes on the road. Say, I'm learning this, maybe I do this the next time, maybe I just do something simpler. If you have a stack of papers and you can get to a copy machine that does a scan for you, a PDF to scan, that can be done. I don't know if the library can do that for you or not, if the copiers in there let you do that with a flash drive or not. But if you have a fax machine, a fax printer and stuff like I have at home, not a real expensive copier, but it can scan. Then you can follow rules that I've got over here on the website. In the website, I have this thing, PDF file extracting and merging. So I have a couple links in here giving you ideas on how to merge and split PDF documents around. So that was a concept that we used last year, and it worked well. Everybody figured out something. So what do I want to do in the closing moments where I'm pretty much blown out of time? Let's see. I did add a lot of info to the website over the weekend, in particular under problem set 1. I now talked about doing the symbolic calculations in Maxima, gave you a sample notebook, gave you a rendered PDF, doing the same thing, similar things in Jupyter. The sum, though, either is done according to the new hints that I posted up for it. See, where are the hints? Right here. Or you can follow the hints that I've given you, but Mathematica should be fine, and of course Maxima works just fine too. So you will get a closed form solution to that problem that is parallels this solution. It'll be something, this is what you're seeking in problem number 1. You're seeking something like that for part B. Something, when I say closed form, it's a piecewise solution. It has the different forms that you get out of it. In this case, it's 2 active forms and then 0 elsewhere is what you're going to have. And the plot will be very similar to this, except it has a slightly different shape with a triangle pulse in there as opposed to this exponential decay. And the way I work through that problem sliding across, very, very similar ideas, almost identical. Has anybody worked on it? Kind of get a flavor for it? You're starting to see some light?
Yeah.
Or do you see total light at the end of the tunnel?
I saw the total light.
Okay.
Problem 1.
Okay, good. Did Maxima or Mathematica help you get a formula?
No. I think I just did it myself.
Okay. I give some good hints on it, though, and I give some results in Maxima of what you could do in Mathematica, so.
Yeah, that's what was helpful.
It's a little bit messy solution. It's not a real trivial thing, and as an engineer, you're saying, I just want, something to have in the whole, like a thing with resistors and capacitors in it. Well, we don't get that here in DSP. We get algorithms and we get, expressions. So that's kind of the way our work is done. And if you think software, that's how we craft software, is we build algorithms and things to do stuff that make our projects a success. So I came up with an idea during a meeting today that I hadn't included. It involves a filtering operation, and the FPGA implementer was saying, I'd like to be able to do this. Another engineer said, we need to have something transition, and I said, I'm going to change the state variable, and I'm going to change something else in the algorithm. And he re-implemented it this afternoon. The build for the FPGA is going to take like 4 hours. Tomorrow morning we're going to be testing it, hopefully in the hardware, and we'll have something that really is going to satisfy the needs for the project. So it does involve teamwork, but it started off as a concept, and then you craft something, and then the implementer implements it. So things that I didn't go through are, in the last problem, I give you lots of hints on it. You're just going to drive a waveform through the first processing block and then through a second processing block. And what you're going to use is the function called lfilt in Python. So lfilt will do like a moving average operation for us very readily. So if we wanted to do something like that, we would set up, and there's examples of filter problems in here where I'm using lfilter. I don't know where one is off the top of my head. I'd have to create one from scratch, but pardon me?
There was one a little bit above. A little bit more, I think.
There it is. Okay. H1 not defined, so I go up here and I find out where is H1 defined right there. Yeah, this is very similar. Well, this is kind of like the homework problem. I think I have it in a notebook, though.
Which homework problem is
The last one, the very last one. You can do it all by hand using convolutions, but I said you can do it by simulation. You can just simulate an input waveform, run it through each block, and then get the output. Is what I'd like you to try to do, because that's kind of a simulation project, and that's a really popular thing for me to do when I'm working on work problems, is do a little simulation of something. Just get an idea of how it's going to work before I send somebody off to coding it. And I see this has got an error in it because this line collection true was something that they had in the library for a while. So if you ever run into an error like line collection true and some of the stuff I have posted, I think I got rid of them, but I might have had an old version on my computer here. So there's an example of a filtering operation. In this case, what the filter is doing is it's mimicking an input, and it's giving me 2 copies of it at the output. So these were the 2 filters that are used, and then the input in this case, I believe, was a -1 to the n, which is an alternating sequence. So it's getting late. I'm getting a little bit delirious feeling. So even though I'd like to get you better prepared, you're going to have to do some studying on your own. So we'll see what happens with the video. It won't be posted tonight, but I'll start looking at it probably, and it'll take me a time to get it up onto YouTube.
And then does the notes chapters, do those correlate with the book chapters?
Yes, they do. Yeah. We get this shut off.